All right, this is 2021 China's Math Olympiad, problem number 9. It is about a series of complex numbers. All right, so this particular series has these following properties. The first element is given, which is a real number here, square root of 3 over 2. And for the remaining sequence here, it's going to be governed by the recurrence relationship. So Zn plus 1, how it's related to the previous one, is the complex conjugate of the number times 1 plus I times the number Zn. Of course, I here is the imaginary unit. We know that it has a property that I squared equals -1, right? That is the unit imaginary. Right, so the question here is to try to find the 2021st element in this series. This is kind of the fill in the blank type of question in the test. All right. So now usually when you have a complex number with a recurrence, sometimes it is easier to use the standard representation of complex number, which is a plus bi. There's another one is a kind of r and theta, right? Like the modulus and the angle representation. But here probably it's easier to work with the standard a plus bi, the real part, and the imaginary part. So let's do that. So let's assume the nth term is actually an plus bni, where a and b are real numbers, right? So this is standard representation of a complex number. So when we do that, the recurrence relation becomes the following, right? So of course, here the first one is the n plus 1th term, and this is the one is the complex conjugate where you change sign of the imaginary part. So this is Zn bar, right? Okay, sorry, not a vector notation here. The software try to be smart, right? It is actually a complex conjugate times 1 plus Zn times I, right? So that's the original one. We just rewrite it with real and imaginary part here, a and bn. Now, of course, we use some algebra to expand this out. So what is the recurrence relationship we try to achieve? So we need to find the recurrence relation. Okay, let's work with some algebra here. All right, let's do that. So here we're going to change it into a plus bi form, right? So for the right hand side, yeah, we're gonna write it. That's the first term. We're gonna keep it here. The second term, however, you're gonna I times an is the ani times bni is an I squared equal -1. So what you get is here for this term, you're gonna get minus bn. So you're gonna have 1 minus bn, right, plus a n I, right? Now you have two complex numbers multiply each other. So this is the imaginary part, this is the real part. So you're going to do the cross product to find out the resulting complex number. So let's do the real part, an times 1 minus bn, right? And then the other part is I minus I times I is going to be -1 with the negative sign in front of it and become positive. So it's plus an bn. That's the real part, right? And then the imaginary part is going to be here. You have bni, you're going to times the real part here. It's just cross product, and there's negative sign behind before that. So it's going to be negative bn, right? 1 minus bn, and the other part, and this with I here. The other part is here, the imaginary part, times the real part an. So this becomes an squared I plus an squared I, right? Now for the real part here, this is the real part here, right? This is the real. And then you can use the algebra to expand it out. An minus an bn plus, they cancel each other. So you want to get is an, right? And then for the imaginary part here, you have an squared, and here you can expand it out. It's become minus bn plus bn squared. So you're going to have plus an squared plus bn squared, and then you have minus bn, and then you times I. All right, so this is the right hand side, and you try to equal the left hand side. When two complex numbers equal each other, then the real part must equal. Here we know that an plus 1 and an has to be the same, and then the imaginary part, which is bn plus 1 equal an squared plus bn squared minus bn. All right, so that's the recurrence relationship we get. One thing here is that you notice that the imaginary part never changes. That's good news, makes the problem easier. Now the first one is a1. We know that it's square root of 3 over 2. So which means every an. Yeah, because every an is equal to the previous term, and then by the recurrence, every an must equal a constant here, square root of 3 over 2. Once you have that, you can plug that in here, an squared. So you can rewrite this relationship, which is, the square would be 3 over 4 plus plus bn squared, right, minus bn. So that's our recurrence relation. We just find it. Here's an plus 1 equal an, from which we know that an is going to equal square root of 3 over 2. All right, I think we're given, let me double check what we got. We're given this, right? All right, good. So now for the bn, however, what you get is bn plus 1 is related to the previous term by a quadratic equation here. So bn squared minus bn plus 3 over 4. So how to deal with that? There's a quadratic. All right, so not very straightforward. But however, if you would do the complete square, you have bn minus bn squared minus bn, right? So if you do that, it becomes bn minus 1/2, and then you have to square it because we complete the square. There is constant term, which is 1/4, so you have minus that, right? Constant term, and then plus 3 over 4. That becomes positive 2 over 4. And this one would be 2 over 4, which is 1/2. So in other words, this is equal bn minus 1/2 squared plus 1/2. Right? You notice that if you were to move these to the left hand side, you're gonna see, maybe a clear pattern here. Bn plus 1. I'm gonna move this to the left hand side, minus 1/2, gonna equal bn minus 1/2 and square. This is a recurrence relationship, and from here we know that bn would minus my half would equal to b1. How is it related to b1 minus 1/2? And then you keep squaring it. Every time you move to the next term, you're going to square the previous term when it says the term is minus 1/2, right? So this quantity here is going to be squared how many times? Almost like n minus 1 times, right? So then so what we get is Zn, right, would be equal to the real part. An is a constant, which is square root of 3 over 2, and the imaginary part, which is bn here, you're going to move 1/2 to the right hand side, is going to be 1/2 plus b1 minus 1/2, and then 2 to the n minus 1's power, and then times I. That's the solution. And so we need to find 2021 here. You plug it in, you get a square root of 2 plus 1/2 plus b1 is actually 0 because b1 is a real number, its imaginary part is 0. So this is selective here, But then negative power is even power, right? It's, here for n greater or equal to 2, right? So this is also an even number here. The power is even number. So this minus here becomes positive. It is the same as positive. So 1/2 to the 2 to the nth power, we can write it here to the n minus 1's power, which is the same thing, right? And then I. That would be the final answer. All right. So here, the trick here is probably this part where you have to complete the square, because otherwise, when you look at this recurrence relationship, it's not easy to work with. But once you figure, you can turn it in a different form. So this is the original recurrence, right? Because we have a square here, minus, this is not easy to work with, right? But if you do the complete square, now you have this form. It's easier to deduce the relation here. Okay, so that's the only trick, and I think all others are just straightforward and algebra. Okay, so hope you enjoy this problem, and let me know if you have any comments, and you can leave a comments here, and please subscribe to the channel. All right, thank you.